right. Yeah, there are. Let's get started. Try to whip through this real quick. First off, let's remind ourselves of what we covered last time. First off, what is a proposition, or the book calls a statement?
When something you know is either true or false.
Yes, it's something that has to be true or false, not both. That's proposition. Something that's true or false, not both. This book calls it a statement. From here on out, I'm just going to call it a proposition, because that's what the world calls it. So, propositions. Now, if we had a bunch of logical operators, things that took propositions and spat out propositions. We had, what was that one?
Or. That's or.
That one's and.
And. That's or.
Or.
That's implies.
Implies.
They both imply.
Logically equivalent. And not. Perfect. So let's fill out this table really quick. So with alpha and beta, if I have two propositions, all the possible combinations is they can both be true. We can have true, false, false, true, false, false. Perfect. So now let's do the conjunction. True and true is true. True and false is false. False and true is false. False and false is false. Good. True or true?
True, false.
Good. True. False. True, vacuously true, and true. Remember, if your antecedent is false, your whole implication is true. And we call it vacuously true. Vacuously true. We're saying if alpha, then beta, right? And if you already know alpha's false, then you can't ever check if every time alpha is true, beta is true. Because alpha is false. So we can't see what happens when alpha is true, because it's false. So we call it vacuously true. There are no cases to check.
So,
like a vacuum, empty. There are no cases.
Okay, let's just break. So, if all cats are black, then all men are mortal, or all men are mortal. Alpha is false, but beta is true. So you're saying it'd be false?
It would be true. Alpha implies beta. It is true that if all cats are black, then all men are mortal. Because not all cats are black. It's vacuously true.
It has to be true, period.
If I'm a purple elephant, then your nose is as long as this building. True. Because I'm not a purple elephant.
Oh, so like you can 2 plus 2 equals 6, then he's the Pope.
Yeah. If 0 equals 1, I'm the Pope. All right. Last one here. Logically equivalent.
Wait, I have one more question.
Oh, go ahead.
And what's that one false? I'm false because it's saying this is true. It's saying,
okay. What does this say? Okay. This says if alpha is true, then beta is true.
Saying if men are
but
mortal,
alpha is true and beta is false. Is it the case that if alpha is true, beta is true?
No, it's not.
No.
It's false.
If alpha is true, beta is true? No. If alpha is true, beta is true?
Yes.
Yes. If alpha is true, beta is true?
Yes.
Yes. If alpha is true, beta is true? Yes. Okay. Perfect. Yep. It's one that you're going to get and then get confused by, and then get again and then get confused by again. All right. Now logically equivalents. Are alpha and beta logically equivalent?
Yes.
Yes. What about here?
No.
What about here?
No.
What about here?
Yes. Yes.
Perfect. And then finally we add not alpha. False, false, true, true. Perfect. Okay, so that was reminding us of our basic logic operators. All right, now we can open this back up. And quickly touch on our review. So review. A statement or a proposition. It's a sentence that is either true or false, but not both. Common operators, not, and, or, implies, equivalent. Some of the basic theorems we proved last time, we proved not alpha and beta is the same thing as not alpha or not beta. When you distribute a not over an and, it turns it into an or. Similarly, when you distribute a not over an or, it turns it into an and. And you can also factor out a not. Remember, you can go the other way. I can have not alpha and not beta, and I can factor out the not, and that's the same thing as not alpha or beta. Similarly, we can factor out the not. So when you distribute it in or you factor it out, you switch your ands to ors or your ors to ands. Finally, we showed alpha implies beta is the same thing as not beta implies not alpha. We had a special name for this implication. Will you remember what it is? It's the contrapositive of that. Okay. And then, before we jump into predicates here, let's remind ourselves. One of the first things I told you is that x plus 2 equals 5 was not a statement. It's not a proposition. Because it depends upon x for its truth or falsity. There's some values of x which make it true, and there's some values of x which make it false. So that introduces us now to what we call a predicate. And so now we're jumping into predicate logic. What's a predicate? A predicate is a proposition-valued function. You give it some term, and it spits out a proposition. You give it some term, and it spits out true or false. A predicate is a proposition-valued function of some amount of variables, maybe one, maybe many. In particular, a predicate of two variables, we have a special name for that, we call it a relation. We talk a lot about relations in mathematics. Relation is one of those words that never goes away. So let's do some examples of predicates. X is brown. This is a predicate, it takes one variable. If I throw that desk into the predicate, I say this desk is brown, it spits out true. If I throw the green board over there into the predicate, it spits out false.
But X is brown, you don't know.
You don't know. It depends on what the X is. So notice that this is like a function. You give me an object, and I spit out true or false.
Right.
If you give me the desk, I spit out true. If you give me that chalkboard, I spit out false. A predicate is a proposition-valued function. It spits out a proposition. You give me a term, I spit out a proposition. You give me a term, I spit out something that's true or false.
So a predicate is not a statement. Can't be a statement.
This is not a statement. Once you give me a term, then it turns into a statement. Once you fill in the variable.
Okay, so it's not a proposition.
It's proposition valued. It's a proposition valued function. Look, you're used to real valued functions, something like f of x equals 2x. Okay, there's a function. If you give the function 1, it spits out 2. If you give the function 5, it spits out 10. This is a real number valued function. For every term you give it, it spits out a real number. A predicate is a proposition valued function. For every x you give it, I could have called this f of x is equal to this predicate. Okay, here's my predicate f. F of x is equal to x is brown. For every x you give it, it either spits out true or false. You give it the desk, it spits out true. You give it the chalkboard, it spits out false. Okay, so that's a predicate. It's a proposition-valued function. It's not a proposition, but if you give it a term, it spits out a proposition. All right, x likes y. Here's one that takes two terms. If you give it Jack and Jill, it spits out true. If you give it Jack and Jane, it spits out false, or whatever. Or true. Maybe they maybe he likes her too. I don't know. All right. Here's a common relation that here's a predicate. This is greater than 2 predicate. So if I put in 5, it spits out true. If I put in -1, it spits out false. So this is greater than 2 predicate. All right. And this is Bob's best friend predicate. If I put in Jack, it spits out true. If I put in Bill, it spits out false. All right, lots of different predicates we can have. Notation. For a single variable predicate, for a predicate that only takes one term, we may write it as some letter representing the predicate and then x saying it takes x. It's the same type of notation that we have for functions here. So we can use this notation to represent a predicate. And if our predicate takes two terms, then we might write it as q of x and y and say it depends on these two variables.
Right.
So we could have done, for the likes here, we could have said q of x comma y is equal to the x likes y. We could have just as easily called it nothing special about q. We could have called it likes there. Nothing special about letters. We could have called this our SpongeBob relation. And that works too. Our SpongeBob relation takes x and y and it spits out when x likes y. So you can put any symbol here you want, and then that shows you what your variables are. And you just do whatever makes sense for your reader. Specifically for relations, it is common to write the name of the relation between the variables like x, q, y. Sometimes we do this just when it's relations. So rather than doing the likes relation like that, we might have just as easily said X likes Y like that, because it reads well when it's a relation. And you're already used to some math. We don't say less than is true for 1 and 2. We say 1 is less than 2. The less than is a relation in mathematics. That takes 2 variables. Okay. So there's predicates and relations. What's a predicate? A function that spits out true or false. A proposition valued function. Perfect. That's a predicate. And then I can't remember the other thing I was going to ask. Oh, what's a relation?
Relation is
a predicate that takes 2 terms.
right.
Okay. Examples. Which of the following are predicates? X is blue.
Yes.
Is that a predicate?
Yes.
Good. Jack is taller than Jill.
That's a relation. No, that's a statement.
It's a proposition.
I mean, proposition.
Statement, proposition, same thing. I'm just trying to get you used to talking about propositions and predicates.
Yeah.
Proposition.
Proposition.
Y is greater than 2.
Predicate.
Predicate. 2 plus 2 equals 4.
Proposition.
Proposition, statement. X loves Y.
Relation.
Relation, predicate. Special type of predicate, a relation. Go home. Proposition, that's true.
No.
Oh, it's false.
Yeah, it's no, it's not.
It's not a proposition. That's not a proposition. That's not a predicate. It's just some words. All right. Next, X is greater than or equal to 2.
That's a relation.
Predicate, not a relation. There's only one variable. This is greater than or equal to 2. If I would have written it like this, X is greater than or equal to Y, okay, now that's the greater than or equal to relation. So there is a difference between those, and it's subtle. All right. X, Y, and Z are triplets. That's a relation. It takes 3 terms. Not a relation, sorry, a predicate. Relation only takes 2. Yeah. Relation takes exactly 2. So it's just a predicate. It's a 3-term predicate.
What if you said X is greater than Y and Y is greater than Z? Would that be a relation?
No, because it takes 3 terms to determine if it's true or false. A relation takes exactly 2. So a relation is just a 2-term predicate. So if it's predicate that takes 1 term, it's a 1-term predicate. If it's predicate that takes 2 terms, okay, we can also call it a relation, or we can call it a 2-term predicate. If it takes 3 terms, we call it a 3-term predicate. It's just relations we work with a ton, so we came up with a special word for it. All right, finally, Jack is taller than X.
Proposition.
That's a predicate, not a proposition. It depends on X.
Okay.
If you give me Jane, it spits out true. If you give me this kid, it spits out false.
Yeah, got it. Okay, I got you.
So it's a predicate. Depending on what you give it, changes the truth or falsity of it. Spits out true in some cases, false in other cases.
In case 1 is less than 2, that's not a relation.
That is not a relation. We can always, if you can instantly call it true or false, it's a predicate. Or sorry, it's a proposition. Thank you. You can instantly call it true or false. It's a proposition. If you have to say, well, it depends on some variable, then it's a predicate.
Right. So that would be a relation, right? There's 2 variables.
This one? This one.
Yeah.
X is blue and Y is greater than 2. That's a relation. That's a is blue and, well, not a nice way to say it. It's a pretty useless relation, but it's a relation. All right. Continuing on, predicates. Now, since predicates are proposition valued, since they spit out proposition, we can use logical operators like and, ors, and nots to construct new predicates from existing predicates. In other words, it makes sense to and predicates together. I could have one predicate which says X is greater than 2. I could have another predicate which says that X is less than 5. And it makes perfect sense to and those 2 things together. Because ultimately, this is proposition valued, so it's going to spell out true or false. This is going to spell out something that's true or false. And so we're anding 2 propositions together once they get their value. Or them, or whatever. Or imply them.
So when you are Would you write a negation of that? Or
Don't worry too much about that for a second. Just focus on the fact that it's okay to use logical operators on both propositions and on predicates. You can still use logical operators, and it makes perfect sense. Okay, so example. Let P of x be x greater than 2. Let Q of yz be y love z. Then we can define a new and fairly useless predicate R, which is going to be P of x and Q of y and z. In words, what is R of x, y, z? What is this predicate? It's the x is greater than 2 of y loves z predicate. And that makes perfect sense. So we can take two existing predicates, add them together, and create a new predicate. Sorry, this notation here, this is how you define a new thing in logic. So I'm defining something new in terms of things that were defined before up there, if that's what's throwing you off. So we're just defining this to be this. Okay, another example. Assume that we have the less than operator for x and y already defined. Sorry, the less than relation already defined. And the equal relation already defined. Then we may define a new predicate, the less than or equal to 1. What do we define that to be? Less than or equal to. Perfectly valid. So you can use existing predicates to create new predicates. This can also be written as x less than or equal to y is logically equivalent to x is less than y, or x is equal to y. Just plugging in the exact definitions of each of those. Or, I mean, plugging the predicate in the middle. Because it's relation. Okay. I think you understand. I just am not saying it good. Okay, quantifiers now. Quantifiers. We have two quantifiers in logic. The first one is called the universal quantifier. It's that upside down A looking thing. We typically read that as for all, for each, or for every. And then we have the existential quantifier, the backwards E, and we typically read that as there exists. So let's read some statements. Example, this says for all x, x is greater than 2. And this one says there exists an x. After we read the there exists, when we go to the parentheses, we always just say such that before we read the predicate. So this says for all x, x is greater than 2. And this says there exists an x such that x is greater than 2. Now notice something here. For all x, x is greater than 2. Is that true?
No.
No. Is it false?
No.
Is every x greater than 2?
Could be. You don't know what x is.
Are all numbers greater than 2?
No.
No. So we can actually call this false. There exists an x such that x is greater than 2.
Wait. Yes.
This we can actually call true. So notice that when you add a quantifier to a predicate, it turns it into a proposition. So x is greater than 2 by itself, we can't call it true or false. But if I say every x is greater than 2, or some x's are greater than 2, you can now call it true or false. So adding a quantifier to a predicate can spit out a proposition. So typically we write the quantifier in parentheses, and then the predicate we're applying the quantifier to in parentheses. Notice that while the predicate x is greater than 2 is not a proposition, both for all x, x is greater than 2, and there exists an x such that x is greater than 2 are propositions. We can now call them true or false. So adding the quantifier to a predicate turned it into a proposition. Okay, we can also chain quantifiers. So let's see, I want to do x plus y equals 0 and x times y equals 0. Okay. So let's do examples with these. For all x, for all y, x plus y equals 0. For all x, there exists a y such that x plus y equals 0. There exists an x such that for all y, x plus y equals 0. And then finally, there exists an x and there exists a y such that x plus y equals 0. We're going to call each of these true or false. And it's understood that the domain we're talking about is for numbers. Okay, So this says for every x and for every y, x plus y equals 0. True or false? That's false. That is not always the case that x plus y equals 0. X could be 2, y could be 4. Okay, this one says for every x, there exists a y such that x plus y equals 0. True. Doesn't matter the x you choose, I can always find a y such that their sum is 0. This says there exists some x such that for all y, x plus y equals 0. That one is false. There is no magic x out there such that for any y you choose, their sum is 0. There is no magic x you can find such that for every y, x plus y equals 0. What is the magic x such that for every y, x plus y equals 0?
Oh, you're saying
Notice that these two are saying very different things. This says that for every x, you can find some y such that their sum is 0. This is saying you can find some magic x such that for every y, their sum is 0.
so it's not saying when y changes, x changes. It's one x.
It's saying there's one x for
So
all y.
let's say negative 100. X does not change.
Right, so you pick your x, negative 100. The only y that makes the sum 0 then is 100. It's not true that every y makes the sum 0. There's only one out there.
Oh, but if you switch those, so
Then it becomes true. This one says for every x, I can find a y such that x plus y equals 0.
It's saying for that.
This one says I can find an x such that for every y, x plus y equals 0. They're saying very different things. So the order of quantifiers matters. Make sense?
Yes.
And then finally, there exists an x and there exists a y such that x plus y equals 0. True. You can find two numbers, x and y, such that x plus y equals 0. All right, let's switch all these to times and do the exercise again. Times, 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 times. All right. For all x and for all y, x times y equals 0. False. Wonderful. For all x, there exists a y such that x times y equals 0.
For all x, there exists a y that x times y equals 0.
Yes.
wait, was x plus y equals 0 true? You say it was true.
On this one?
Yeah.
Top
On this one? Yeah. For every x and for, or no, we said it was false. For every x and for every y, x plus y equals 0, that's false. I might have accidentally written a t there, I don't remember, but.
For every x, there is y.
For every x, there exists a y such that x times y equals 0?
True.
True. Now, there exists some magic x such that for every y, x times y equals 0?
True.
In this case, it's true, and that magic x in this case is 0.
But if you were to change 0, that would not be true.
Yeah.
Right, if we were to make this a 1, that's no longer the case. What about if we made this one a 1 up here? Would this be the case? For all x, there exists a y such that x times y equals 1.
Yes.
Yeah.
And that would be y equal to 1 over x, right? If you choose x, I pick y to be 1 over x, and then their product is equal to 1, right? No. One exception, 0. 0 times what equals 1? 0 times 0 equals 1?
I'm saying nothing.
Nothing.
No answer.
So it is not true that for every x there exists a y such that the product equals 1.
So that's
There's one x that it won't work for. That's when x is 0. Okay, I think you guys are getting this. And then finally, there exists an x and there exists a y such that x times y equals 0. True. Perfect. Okay, so there's some example using these quantifiers.
Existential quantifier almost always true. There exists an x and there exists a y, whereas they equal something.
That's just saying that you can find two of them that doesn't. You can pick the same one twice and that's perfectly fine. Did we do this? Or did we not do this? No, we didn't. Definition, let P of x be any predicate. Then for all x, P of x is a proposition that is true if and only if P of x is true independent of x. In other words, for all x, P of x, this whole thing is true if and only if P of x is always true. That's what it means it's true for every x. It means it's always true no matter what x you choose. For example, let's say that P of x, we define this to be the x or not x. Yes. So our function takes in propositions and it spits out a proposition. Is it true that for all x, x or not x? Yes, it is. The sky is blue or the sky is not blue. The grass is green or the grass is not green. The answer is 6 or the answer is not 6. For every x, this is true. So for all x, p of x is true. How do we know? Because it doesn't matter what x I plug in there, it always spits out true. That's what we're saying. Let p of x be a predicate. Then for all x, p of x is a proposition that is true, if and only if p of x is true independent of x. For any x you choose, p of x is always true. For any x you choose, p of x is always true.
Right, but it depends on what p of x is. Unless that is always
Right.
p of x.
If p of x is something that's true no matter what you choose, if it's a predicate that's true no matter what x you plug in, then for all x, p of x is true. If it's not true for whatever x you choose to plug in, then for all x, p of x would be false. That's how we're defining the truth or falsity of these statements. When is for all x, p of x true? When p of x is true for every possible x. When is for all x, p of x true? Or when is it false? When it's not true for every possible x. Correct. So, here's an example. Let's say p of x is greater than or equal to x. Is it true that for all x, x is greater than or equal to x?
It is, because it says
It is.
Oh, yeah, it's true.
It is true. So this is a proposition, and it is a true proposition. Because this inner predicate is always true for any value of x.
Wouldn't it be vacuously true or whatever?
Vacuously true? No, that only applies to implications. Now let's look at this one. For all x, x is greater than or equal to 2. That's false, because there are x's that make the predicate false. Okay. Next definition. Let p of x be a predicate, then we define there exists x such that p of x to be not for all x, not p of x. This is our definition. What do we mean by there exists an x such that p of x? We mean it is not the case that for all x, we don't have p of x. Let's put that in English so that you can see this both ways. There exists a swan. There exists x, there exists a swan. We're pretending that our domain now is swans. There exists a swan such that it is black. So P is black predicate. So there exists a swan such that it is black. Says the same thing as it is not the case, that's the not, that for every swan, it is not black.
Right. Yeah, it's just double negative.
Kind of. So there exists an x such that p of x says the same thing as not for all x, not p of x. There exists a swan such that it is black says the same thing as it is not the case that for every swan it is not black. Well, the point is to just see that these two say the exact same thing.
Right.
This says the exact same thing as this. That's the point. In general, there exists an x such that some predicate, p of x, says the same thing as it is not the case that for every x, not p of x. These say the same thing. There exists an x such that p of x says the same thing as it is not the case that for every x, not p of x. Theorems that we're not going to prove, but try to get to appeal to your intuition, and then you're going to see how to have a much easier time negating some of these statements that threw you for a loop in your homework. So theorem, if p of x is a predicate, then for all x, p of x is the same thing as not there exists x such that not p of x. Let's pick a statement. What should we pick our p of x to be in each of these? we'll do X is black. And we'll pretend that our domain is swans. So this says every swan is black. Is logically equivalent to it is not the case that there exists a swan that is not black.
Right. Makes sense.
Every swan is black. It is not the case that there exists a swan such that it is not black.
What about, oh,
Right.
oh,
Okay? Negate both sides and we get this. Not for all x p of x is the same thing as there exists an x such that not p of x. This says not all swans are black. This says that there exists a swan that is not black. Not all swans are black. There exists a swan that is not black.
Very true.
And then
So
going from here to here,
we're upside down A and upside down E opposite each other.
I don't want to say opposite. Opposite is such a dangerous word.
Contradictions.
They're not contradictions of each other. They're just two different quantifiers. It's true.
Saying like if you apply the not to it, it's turn it to an A.
So, perfect. So the same way that we have not alpha and beta
so
Equals
you have
alpha and or beta.
gives us, also equals, gives us not alpha or not beta. We also have that not for all x p of x. When you distribute the not over the quantifier, it turns a for all into a there exists. And then you can put it inside. So if you want to put the not inside, you switch a for all into a there exists, a universal into an existential.
are no black swans, period.
Hold on. And then same thing, distributing a not over an existential. Not there exists p of x. When you distribute that not, it turns the existential into a universal, and then the not goes on the inside. So this is what everyone's doing in their head when they're reading statements like this. So this is saying all men in Georgia are at least 6 feet tall. This is of the form for all x, not p of x, or p of x, right? All men in Georgia are at least 6 feet tall. P is a at least 6 feet tall predicate. So for all x, p of x, that's what this is saying if we were to symbolize it. You with me so far?
Yes.
Now we want to find its negation. We want to find not for all x, p of x. And its negation is there exists x such that not p of x. Its negation is there exists, or some, there exists and some are the same thing, some x are not p of x. So what's the negation of all men in Georgia are at least 6 feet tall? Some men in Georgia are not at least 6 feet tall.
Why on the second theorem you say that those two apply each other?
They're logically equivalent.
They're logically equivalent. Right.
This is logically equivalent to this, and this is logically equivalent to this.
Right. You're trying to give the negation.
Right, so here's our statement,
Okay. Okay.
and then here's the negation of the statement, and now I tried it out with the sum language.
Okay, I got you.
So let's do it again. All students in France like geometry. Let's write this with our logical notation. This is saying for all x likes geometry applies to x. Right?
Right.
That's what this statement says.
Negation, it'd be
We want to negate that, so we want to see what not for all x.
this, at least one student that is not like geometry.
So that would be there exists x such that not likes x. There exists an x such that they don't like geometry. Or some students in France don't like geometry. Same thing. So that's how we do this in our heads. Every rectangle is square. That's saying for all x, the square applies to x. The is square applies to x. If we're going to negate that,
There exists a rectangle that is.
there exists an x such that not square applies to x.
Right.
You got it?
Yes.
You write down the rest.
Let's read the next one. Every circle has a center. What's the negation of that?
Some circles do not have centers.
Right. There exists x such that not having a center applies to x. Or some circles don't have a center.
There exists a pair of numbers.
Or there exists a circle that does not have a center. All right, next. For every pair of numbers A and B, so this one is saying that for all A comma B, then A plus B is equal to B plus A, right?
Yes.
And we want to negate this whole thing. We want to find out what the negation of this statement is. Well,
There exists
perfect.
numbers A and
We
B
switch
that
that to
not-
there exists A and B such that A plus B
does not equal B
is
plus
not equal to B plus A, and then negate the inside. Swap your quantifier, negate the inside. That's how you distribute a negation. Some men play golf. That would be written as there exists X such that playing golf applies to X. If we were to negate that, what would that be? We switch the there exists into a for all.
No,
So that would be for all X, not
men
golf,
do not play golf.
applies to X. So you said it right. For all X, it is not the case that they play golf, or no men play golf. A lot of ways in English you can say it. The important part is going to be for you to be able to, one, represent the statement with this type of notation, and then negate it to this. That's going to be the crucial part. Not the 6 different ways in English you can say the same thing. There's at least one number X such that X plus 3 equals 7. So that's saying that there exists X such that X plus 3 equals 7. We want to negate that.
That means
Switch the existential quantifier for a universal quantifier, and then negate the inside. For all X, X plus 3 is not equal to 7. Or there is no X such that X plus 3 equals 7, but it's a harder way to say it. Okay, so there's examples with the quantifiers. Proofs. So every field of mathematics is simply determining the logical implications of the given field's axioms. So all of geometry, when we get to geometry proper, we're going to be given a bunch of axioms. And throughout the whole course, pretty much all we're doing is we're looking for the logical implication of those axioms. So we're going to see that alpha and beta together imply some other statement here. We're going to see that these two together imply some other statement here. We're going to see, oh, if I take this thing right here and that right there, those imply some new statement. And we're going to call those theorems. So every field of math is essentially just proving a bunch of theorems. All proofs are just demonstrating that given some set of assumptions, some conclusion follows.
what's the difference between proof and theorem?
You prove a theorem. So there's 2 ways to think about the theorem. I don't want to confuse you on that language there. The way that you validate a theorem is true is with a proof. So the Pythagorean theorem says that if you have a right triangle, then the sum of the squares of the legs is equal to the sum of the square, or is equal to the square of the hypotenuse. That's a theorem. We know the theorem is true because we proved it. So you need to prove a theorem is true to call it a theorem. Okay. Anyway, so that's what math is. All proofs are just demonstrating that given some set of assumptions, some conclusion follows. Common proof styles. Common proof styles easily verified with alpha implies beta truth table. If you know alpha and you know alpha implies beta, then you know beta.
Right.
If I know alpha and I know alpha implies beta, then I know beta. So common proof is going to be, well, should I write out the whole truth table for this, or is this a bit dense right now? Let's write out the truth table for just one of these one time, and then we'll do it from there on out. So we need an alpha, we need a beta, we need a alpha implies beta, we need a alpha and alpha implies beta, and then finally we need a alpha and alpha implies beta, all implies beta. Okay. let's whip this out really quick. We can have true, 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 false, false, true, false, false. Really quick, shut that. Okay, true implies true is? True. True. True implies false is? False. False implies true? True. False. True. True. Okay. Now we're anding these two together. Alpha and alpha implies beta. True and true is? True. True and false is? False. False and true is? False. False and true is? False. Perfect. Now, here, we're showing that we're doing this implies this. Alpha and alpha implies beta, all implies beta. Maybe put outer parentheses like that in case it's confusing what we're saying. We're saying that whole thing implies beta. Okay, so let's write this out. True implies true is? True. False implies false is? True. False implies true is? True. True. False implies true. Back to true. False implies false is? True. Notice that this is always true. It is always the case that if you know alpha, and you know alpha implies beta, then you know beta. That is always the case. And so this is the outline of what you do in a theorem. You take your alpha, and if you show that alpha implies beta, then you know the beta. So going back, our axioms, one of these axioms is going to be like an alpha. One of the things that we're trying to prove is going to be like a beta. If I know alpha, and I show that alpha implies beta, then I can conclude my beta. And then I can work with it from there. So that's the overall outline of how you do all your proofs, written out in logical notation. And then a similar thing is, if you know beta, and you know alpha implies beta, then you know not alpha. In simples, not beta and alpha implies beta gives us not beta, or not alpha. Remember, alpha implies beta is the same thing as, this is the same thing as not beta, and we can write the contrapositive of that. Not beta implies not alpha. All implies not alpha. If I know not beta, and I know not beta implies not alpha, then I know not alpha. Using contrapositive. So common proof techniques, you'll get way more used to those when we actually start delving into proofs, but I'll show you the logic for them at least once. Okay. Next one. Example. The notice said, if it rains on commencement day, then the graduation ceremony will be held in the gym.
If A, then B.
That says if alpha, then beta. What's alpha? It rains on commencement day. Beta is the graduation ceremony will be held in the gym.
If it rains.
Right. Today is commencement day.
And it is raining.
And it is raining.
That means alpha is true. That means that the graduation will be in the gym.
Therefore, since both alpha implies beta is true and alpha is true, we know for sure that beta must be true. Or in other words, the graduation ceremony will be held in the gym is true. And we're guaranteed that. Because alpha and alpha implies beta, all implies beta, we showed is a tautology. It's always the case. If you know alpha and you know alpha implies beta, then you know beta. We showed that's a tautology. It's always the case. Okay. Jim claims that negative 3 is a root of x squared minus x minus 6. Or in other words, sorry, I said this kind of bad. What does it mean for negative 3 to be a root of this? It means negative 3 makes it equal to 0. So Jim is claiming that if you plug in negative 3 to this, you'll get 0. Or Jim is claiming negative 3 satisfies this. You with me so far?
Yeah. He was saying x equals negative 3.
If x equals negative 3, then x squared minus x minus 6 is equal to 0. That's Jim's claim. So, now look at it. If negative 3 is a root of this, then that means when you plug in there, negative 3 squared minus negative 3 minus 6 has to equal 0. That would be alpha implies beta. However, negative 3 squared is positive 9.
Positive 9.
Positive 9 minus negative 3 is positive 12. minus 6 is 6.
So it's not 0.
So beta is false.
Therefore,
Therefore,
James is wrong.
since both alpha implies beta and not beta are true, we know that alpha, or negative 3 is a root of x squared, is false. Or in other words, that not alpha is true. So there's an example with each of those. Okay. Lastly, we have the law of identity, and then we're done. So we did propositional logic, propositions, things that are true or false, not both. Propositional logic, you just basically have propositions, and then you have and, or, not, implies, and logically equivalent. Together with proposition, that's everything you say in propositional logic. In predicate logic, we add predicates, so things like p of x, and we add quantifiers for all and there exists. That's predicate logic, adding those. Now we're going to add identity to our logic, and then we'll be done with logic. So the law of identity gives us two rules that we can use when we use this special symbol equals. Equals is a very special symbol. If we're using that very special symbol equals, we instantly know two things about it. So law of identity. Everything is identical with itself. This is our first law of identity. It's not something we prove. It's something we accept without question. Everything is identical with itself. It is often also stated as A is A or A equals A, but the most proper way to say it is for all x, x is equal to x. That's always true. We can always accept that as true. Next is the principle of existentiality. It's part of the law of identity. But in short, it says equals may be substituted for equals. Let's do an example. Theorem. If A equals B, then A plus C equals B plus C.
If 4 equals 4, then 4
Let's
C
redo this really quick. Get rid of plus here, and let's replace this with oh, never mind. We do that down here. So if A equals B, then A plus C equals B plus C. How do we know that? If A equals B, so if I know A equals B,
4 equals 4.
I'm trying to prove this equals this. Giving an example doesn't work. Notice, is A plus B equal to, A plus C is equal to A plus C. This is always true. How do I know?
Because A is equal to A. C is equal to C.
Because they're the same variable.
Because of the law of identity.
Because of the law of identity. Look, I have some symbols over here equals some symbols over here. Those symbols are identical.
Right.
Everything is identical with itself.
Right.
So I know that this is true from the first law of identity. Using the second law of identity, that says equals may be substituted for equals. I know that A is equal to B. I know A plus C is equal to A plus C. Substitute in one of those A's for B, I get B plus C is equal to A plus C, using the second law. So I know this from the first law, and then if this is the case, I know this from the second law.
Right.
So that is how you prove A plus C is equal to B plus C. It is not a proof you do in arithmetic, in algebra. There is no algebraic proof for this. This is a proof of logic. It's more fundamental than that. Similarly with times. If I would replace this with times, notice A times C equals A times C is always true. It has nothing to do with what times is. Times is completely irrelevant. The point is, I have identical symbols, identical symbols.
Right.
Identical symbols are always equal with identical symbols.
Right.
That's the first law of identity. Everything is identical with itself. Second law says, if I know that these are equal, then I can substitute it out. And I get B times C is equal to A times C. Equals may be substituted for equals.
Right, because A equals B.
Right. So in general, if A equals B and circle is an operation where A circle C and B circle C are well defined, so they make sense. We're not writing nonsense. As long as this makes sense and this makes sense, then we always know that A circle C is equal to B circle C. For any operation, for any A, B's, and C's. A, B's, and C's here could have been functions, and that operation could have been function composition. They could have been matrices, and that could have been matrix multiplication. It doesn't matter what it is. This is always the case. We know that, not from any proof in mathematics, it's more fundamental than that. We know that from the logic of it. So that's introducing the law of identity, those two rules. And with that, we finish up everything we're doing with logic. Next week we'll do set theory. These are some of your homework problems that I wanted to do a couple of just to give you a feel for how to do some of these. So eventually this is going to be on your homework down the road. I think it's not your homework until not this week, but the week after. But let's say that we have some axiom 1. Here's assumption 1. For all integers a, b, and c, if a plus b equals a plus c, then b is equal to c. We're going to take that for granted. That's axiom 1. Axiom 2 says for all integers a, b, and c, if a times b equals a times c, where a is not equal to 0, then b is equal to c. Now we're going to prove one of these statements. Okay, so I'm going to formally write out a proof now. First formal proof. Proof. If x equals 5, then 3x plus 4 equals 19. We are now going to prove that statement is true. Okay, step 1. When you're proving an implication, you always assume the antecedent. I'm trying to show that if this is true, then this is true. So assume this is true and show that implies this is true. So 1, assume x is equal to 5. 2, then 3x plus 4 is equal to what?
19.
How do you know? You're skipping a lot of steps. Let's do one piece of logic at a time.
Oh, then we know it's equal to 9. X equals 5.
So I can, using law of existentiality, I can substitute out the x with the 5. We just used a theorem of logic. So using a theorem of logic, I now know this is the same thing as 3 times 5 plus 4.
You have to write down, use the theorem of logic.
We won't write down every time we use a theorem of logic. We will write down when we get to geometry every time we're using a theorem of geometry. I just want to make it very explicit. I want you to not rely on your intuition, oh, duh, this is obviously true. I want you to stop and think about all the pieces of logic precisely that you are using so you can justify every step. So when someone says, how do you know that you can just plug a 5 in right there? You say, oh, well, that's just what you do, like an algebra student would say. No, tell them exactly. We assume the second law of identity that says equals may be substituted for equals. So this may be substituted for that using that rule of logic. Make sense?
Yeah.
Seeing the rules is the important part. I trust you can do the algebra. Okay. So now we can multiply those together. 3 times 5 by definition is 15. Plus 4, we won't go over definitions of numbers, but you'll take my word for it. And then 15 plus 4 is 19.
So in geometry, are we going to have to go over the definition of numbers?
No, because you don't work with numbers in geometry. You work with geometric figures. Numbers would be if we were doing algebra. All right, so there would be our proof on how we do this. And then square box is, it used to be, oh, what were the 3 letters? Square box just means, and thus is demonstrated. It just makes it very clear to the reader that we have reached the end of the proof. So let's do another one of these. So that was an easy one. Let's look for one that's a little bit harder. Let's do this one. Notice that this one's going the other way. We're not saying if x equals 7, then 4x plus 5 equals 33. That would be easier. Now we got to go the other direction. Okay. So proof. We are proving that if, which one do we pick? 4x plus 5 is equal to 33, then x is equal to 7. All right, how are we going to prove that? We're proving an implication. How do you prove an implication? Assume the antecedent and show that implies the conclusion. So assume, or let, we usually say let 4x plus 5 equal 33. Okay, now what am I going to do?
Now you're going to minus 5 off the side.
I'm going to subtract 5 from both sides. So I can say then 4x plus 5 minus 7 is equal to 33 minus 7. How do I know that?
Why minus 7?
I don't know. Good question. How do I know I can subtract 5 from both sides?
Because the law of, same thing on both sides. I don't know what it's called.
We're using the law of identity again. We're using both of them in one go. Always and forever, I know this. 4x plus 5 minus 5 is equal to 4x plus 5 minus 5. How do I know that this is always the case? First law of identity. Everything is identical with itself. Now I know 4x plus 5 is equal to 33. So I can substitute 4x plus 5 with 33. That's using the second law of identities. Equals may be substituted for equals. And so it's using those two laws of identity that we can justify adding the same thing to the both sides or subtracting the same thing from both sides. So we just use both those laws of logic in one go. Again, you don't need to explicitly say it in your proofs. That becomes kind of tedious, writing out every piece of logic that you use, but it's important that you see it. Okay, so now we know that. Well, we'll just keep manipulating here. So then 5 plus negative 5 is obviously 0. 4x plus 0 is just 4x. So simplifying, we get this is equal to 28. Right? Okay, now what? Multiply both sides by 1/4. So 1/4 of 4x is equal to 1/4 of 28. 1/4 times 4 is? 1/4 times 4 is 1. So that just leaves us 1x, or x is equal to 1/4 times 28 is 7. So we get x is equal to 7. And thus it is demonstrated. Square box. All right, let's do one more. You guys pick which one you want to do. 7?
Wait. Ooh, 9.
Let's do 9.
9?
19.
9, an if and only if? Okay.
Which was the hardest one?
I don't know.
You look. Yeah.
7 might be the hardest because of the language. 9, if you're not comfortable with the if and only if. I think they're both good options. So 2x plus 7 equals 19, if and only if. Thank you. If and only if 4x minus 3 equals 21. Okay. So to prove an if and only if, I need to show that this implies this, and then I need to show that this implies this. So first I'm going to prove this implies this. I'm going to prove the forward direction. Sometimes when we're proving if and only ifs, we put an arrow like that in parentheses to the side to tell the reader, hey, first I'm proving this way. So I say let 2x plus 7 equal 19. You with me? Okay. So, huh? It means I'm proving this way. I'm going to show this implies this, and then later I'm going to show this implies this. So it's like you're doing 2 proofs in one go. Okay. So let 2x plus 7 equal 19. 2. Then subtract 7 from both sides. We won't bother writing that out now. Then 2x is equal to, what's 19 minus 7? 12. And 2x equals 12 implies x equals 6, right? And if x equals 6, then 4x minus 3 is equal to 4x minus 3 is equal to, what's 4 times 6? Minus 3? 21. Okay, we did it. We showed that if this is true, then this is true. Now I need to prove it the other way. So now I need to prove it this way. So now we let 4x minus 3 equal 21. Then subtract 3 from both sides. We get 4x is equal to what? Oh, what did I write? Oh, no, I didn't do that right. Not subtracting from both sides. Add 3 to both sides.
Oh, yeah, okay.
Sorry about that. 24. And that gives me, if 4x is equal to 24, x is equal to 6. 6. Then 2x plus 7 is equal to 2x plus 7 is equal to 2 times 6 is? 2 times 6 is 12 plus 7 is 19. 7. Therefore, 2x plus 7 equals 19 if and only if 4x minus 3 equals 21. And we're done. I showed the left implies the right. I showed the right implies the left. Therefore, they imply each other. Okay, so that's how you prove an if and only if. So we'll do a few more of those exercises next time. Can't keep you too long. Unfortunately, we had to get a late start. And then we'll get into set theory. Any questions that you want answered, recorded?
You can throw this away.
You can do whatever you want with your homework. You may want to keep it for the sake of studying for tests.